signature register. Single input signature register. We are applying clocks, and this is the input from the circuit and the test. We are applying clocks to this guy also. The question is, we apply some n inputs, right? N inputs. N input vectors. Start with let us say reset of the SISR. Then when we stop after n vectors, the good circuit leaves behind is, let us say, 1100, and the faulty circuit signature is also 1100. Okay. So if that happens, we say there is an aliasing. Okay. See, if you have a m bit register, there are 2 to the power m signatures possible. So after applying n test vectors, one of these will be in the the good signature registers, right? What is the chance that the faulty signature also is the same? So this is there are 2 to the power m inputs in this set. Okay. Each of them corresponds to a signature. Maybe this is 1100, this is 0101, and so on. Now the good signature is this. What is the chance that the faulty signature also maps to this? Okay. You will possibly agree that if m is large, then the chance of such a thing happening is very low. The probability of aliasing is low. If the sort of the cut outputs are sort of fully uncorrelated to one another, right? Then this probability may be like 1 by 2 power m, okay, where m is the length of the signature register. So if you have taken m to be a large number, like 32 bits or something like that, then the chance of that aliasing is very low. Okay, so aliasing probability is 1 by 2 power m, and that is sort of low. Okay, so that is what you have to appreciate. Now we'll take what is called as a multiple input signature register. As the name itself indicates, such a signature register will have not one input but many inputs, and it will have m is the number of flip-flops. Okay, so it will have m outputs, and it has many inputs. So how do we build such a thing, right? So we could take our shift register, so here is my circuit and a test. Let us say it produces 4 outputs. So what I can do is, earlier I was taking this output, right, and this guy here, and I was XORing them, right, and then I was sort of bringing that as an input to this guy. Okay, I would connect this guy here. Now what I can do here is, I can take the output here and XOR these two guys together and feed that to this guy. And similarly I could take this output and feed these two guys, and then take the feedback output, take the feedback output. Okay, this is a multiple input signature register. Okay, so I think I will illustrate this in our circuit verse so that it is clear to you. So this is a single input signature register. Okay, so we'll modify it a little bit. Okay, we'll remove this AND gate and these two guys. So I have taken the the XOR of last two inputs, and here is my circuit and a test. So let me make a circuit and a test here. Let me pretend that the circuit has maybe a decoder or something like that. This is a decoder. Okay, so we can take it to have 4 bits. So this is a 2 to 4 decoder. Okay, so it has 2 inputs and 4 outputs. So we'll take 2 bits and connect them here. Okay, so it is going to decode these guys, and so I'm still, oops, sorry, I'm going to still take the XOR of these guys. But what I'm going to feed to this guy is the XOR of this feedback line. So I have taken the XOR of the last 2 flops, and I'm going to take the XOR of this output and this guy. So take an XOR gate. and that should go here. Is that clear? So I'm taking the XOR of these two bits. That will go everywhere. The 0th bit I am XORing it with this guy over here and fitting it. In the same way, the XOR of these two guys that should go here. I think this is the problem here. Okay. And last but not the least, another XOR gate. And this guy over here will be so reset. Okay, and let us say initially the input is 0 0. Okay, this is a good decoder, so this output will be 1 and all others will be 0. Okay, so this is a good decoder. 0 0 0 1 1 0 1 1. That is how the inputs will change. So I have got as 1 here, as 0 here, as 0 here, as 0 here. And now when I lower the reset, okay, and then I clock it, this guy got loaded with 1. Okay, maybe the input continues to be 0 for one more clock cycle. So when I clock it again, this time the input will become 1 0 1 0. Then again one more clock cycle 1110, again one more clock cycle 1110. Okay, so it seems to be in this 1110. Okay, now the inputs may change. So that is how the signatures are changing. So let us start all over again. Let us start with 00. Okay, I have reset the signal. I'll go back to reset equal to 0. Now what I'll do is I'll change 00011011 like that. Okay, so this is 00. Then let us say 01. Then 10. Then 11. So 1100 seems to be the signature of a good circuit. Okay. Now let us create a fault. Let us inject a fault here. So let us pretend that this guy is stuck at 1. So we'll reset the circuit again and apply 00 again, right? And then lower the reset, apply clock. So you can see that it went to the 0011 state because of the stuck at 1 fault. Then I will change the input to 01 and apply another clock. So it went to 0010 state. Then I will put 10 and apply another clock. It went to 1101 state. And now finally 11. So it went to 0101 state. Okay. So the good circuit had gone to 1100 state. The stuck at 1 fault here sends it to 0101 state. So even 4 clock pulses will be sufficient to detect that there is something wrong with the circuit. Okay. But if you continue to apply a lot of clock pulses, etc., there is a small chance, okay, that at some point the good and the faulty circuits will be identical. Okay. For the same set of inputs, the good circuit and the faulty circuit produce the same signature. So if that happens, we say there is an alias. Okay. So this is a multiple input signature register. Okay. All right. So what a best circuit will do is, so logic based, for a big circuit, so they'll take a PRPG, pseudo random pattern generator. They may put a phase shifter here. Then the outputs of these will come to the circuit under test, right? And if the circuit has scan inputs, okay, then one way to do this would be to feed this to the scan chains. So we can use the random patterns and scan the random patterns into the scan chain. And then that is during the scan enable. Okay, scan enable is equal to 1. That means we are shifting in the patterns into the scan chains. Then we go into the test into the capture mode, normal mode. So that is SC equal to 0. So capture the response. So these, depending on whether the circuit is good or bad, a different response will be captured into the scan chains. Then scan out the response. And these responses will be compacted using the multiple input sequences. And compress compression using MIS. So in a large circuit, which is a sequential circuit, that is one way to perform best. Okay, this is one architecture, one possible architecture for logic best. There may be others, okay, but this is one possible logic best architecture. So we will go ahead and simulate the good circuit and note down what is the signature register, and then apply the test patterns to the hardware. And if the signature that we got was different from the good circuit signature, we will declare that there is a fault.